is so-called Cmax, the maximum concentration after the dose, and then that corresponding time down here is so-called Tmax. So I want to talk about calculation of Tmax and Cmax. I already gave you the equation in the lab or whatever. But Tmax, that's the time where we get the maximum concentration. So Tmax is simply equal to, what kind of units would Tmax have? Time units, right? It might be hours, minutes, seconds, but it's going to have time units, okay? So Tmax is 1 over Ka minus Kel times the natural log of the ratio of Ka to Kel. Okay. Tmax. So that's this value down here on this axis. That's the time again when I reach the maximum plasma concentration. Because remember, at times before Cmax, I'm in the absorption phase. Okay. The concentration is going rising up to Cmax, and then after Tmax, the concentration starts going down. And then in your textbook, at least it used to be in your textbook. I haven't looked in this section in a while, I must admit. But they have an equation. At least they used to have an equation for Cmax. But to me, it was overly complicated. So to get Cmax, that's this concentration here. Okay, the maximum concentration. You don't just look at the data set and pick the highest concentration in the data set. That ain't the way you do it. The highest concentration in the table or the data set, like in your textbook, the problem we worked on in the lab yesterday, that highest concentration may or may not correspond to the true Tmax value. Certainly Tmax is going to be in that area, but remember those are discrete points. I'm just drawing a solid line here. But when you're looking at your data set, you have a series of concentrations in data. So don't just look at the highest concentration and say, well, that's Cmax. And the time associated with that concentration, I'm talking in a table, a set of data, and say that time is Tmax. Oftentimes that's not going to be the true Cmax and Tmax. So calculate it. It's going to be, the Cmax in that table is going to be close to the true Cmax, but it might not be Cmax. Because they might not have taken a concentration at the actual Tmax value. Okay? Cmax, just use your equation for concentration. So the equation that says F times D times Ka over V times Ka minus Kel. I'll look in the textbook and see if they still had that complicated equation, but you don't need it. Just remember this equation, e to the power negative Kel. And for T, put your calculated Tmax there, Tmax. Okay? Because remember we said that equation covers the entire plasma concentration time curve. So Cmax is on that curve too. And then this is minus e to the power negative Ka times whatever you calculated for Tmax. That will give you your Cmax value. Okay. So you don't need to memorize a new equation or whatever. Just put the Tmax value in the equation that you already are familiar with. That'll give you corresponding Cmax. Questions? So that's Tmax and Cmax. We okay? I'm sorry? Oh, okay, I'm getting fat. Stop eating. Okay, so Tmax and Cmax, two very important, relationships that pertain to this particular model. Let me see. Now, so far with this model, we talked about the normal case, that is where Ka is usually greater than Kl. Because usually for most drugs, the efficiency of absorption is greater than the efficiency for elimination. In other words, drugs absorb, generally speaking, drugs absorb more easily than they are eliminated. So that makes Ka usually a greater value than Kl. That's the normal case. That's what you're going to see better than 90% of the time. Most of the drugs on the market that you'll dispense or whatever, prescriptions, most of those drug products will have a Ka that's greater than Kl. That's the normal situation. There's a second situation. That no signal is going to mess me up. I'm going to pull this over just a little bit. Let's see if I can get most of this board. There's a second situation where I'm going to say case where Kel is greater than Ka. Okay. So the normal case is Ka is greater than Kel. That's what we usually see for most drug products. Okay. But we have a situation where Kel is greater than Ka, and when that occurs, we have what we refer to as the so-called flip-flop absorption model. Flip-flop absorption model. Okay. The relative sizes of Ka and Kel are reversed, so it's called a flip-flop. Now, the flip-flop absorption model, guess what? The plasma concentration time curve is going to look just like this. It's going to have an absorption phase and an elimination phase. Okay. So this initial phase here is still the absorption phase. The concentration is still going up because absorption is occurring faster than elimination. Here, when it's going down, elimination is occurring faster than absorption, so the concentration is going down. So all of that stuff we learned about the normal situation is still true. But here's the kicker. In laboratory, we learn how to feather the curve and get Ka and Kel. And we're going to do the same thing today for the Winters group, okay? So we're going to take this curve and, as Dr. Poppian says, break it down, okay, to the ground. For the flip-flop model, though, this post-absorption phase, okay, if we back extrapolate it, let me just do another one here. So we look at the concentration time curve. When we back extrapolate that post-absorption phase line all the way back to the y-axis, okay, the slope of that line is equal to Ka, negative Ka, not Kel. You get the slope the same way as you would be looking for Kel, but you set that slope equal to negative Ka. And then when we strip the curve, like we learned how to do yesterday, and like I talked about in class, okay, but we're going to actually do it in the laboratory. When we strip the curve, we get our residual line. The slope of the residual line is equal to negative Kel. You get those lines the same exact way as you did in the normal case. So in this case, Kel, okay, you will find is going to be greater than Ka when you find the slope and set it to equal to negative Kel. It's going to be greater than Ka. So-called flip-flop model. A lot of drug products that are being developed often don't get to market because they show this flip-flop absorption characteristic. I think they do give some examples in your textbook of drugs that are on the market. I'm not holding you responsible for that. I just want you to know that this can actually occur. A lot of those drugs that don't make market, show this characteristic, and a lot of drug companies decide not to pursue the research and development further sometimes because if Kel is greater than Ka, that means that the elimination half-life is much shorter than the absorption half-life. T1 half equal to 0.693 divided by Kel. T1 half of absorption 0.693 divided by Ka. So the elimination half-life is shorter than the absorption half-life. So if you have a drug with an elimination half-life that's real short, that means that patient is going to have to be taking that drug more often if it has a short half-life. So that can lead to compliance problems, or what's the new term? Adherence problems. I don't know why they keep changing the language. I mean, compliance. Somebody here might know why they changed from compliance to adherence. Anybody know? They just do it just for the help. It used to be non-compliant. Now I guess it's non-adherent. But what compliant was just too bad of a sounding term or something? I guess nobody but me has ever thought about that. But I'm like, compliance was fine, but now it's adherence. But anyway, if the absorption half-life is real short, you don't want the patient having to take a drug every hour, every 2 hours, whatever. So usually dosing them over 4 hours, 6 hours, 8 hours, 12 hours, and every 24 hours. So you don't want to put something out there on the market where you're telling the patient, they need to take this tablet every 2 hours or every hour because of this short half-life or large KEL. Okay. But there are some drugs out there that there was not much of a choice. Some drug products, and they will show this characteristic. Yes?
Here we can say post-absorption phase is a absorption phase?
No, it's still called the post-absorption phase. This is still the absorption phase. Okay. It's still the absorption phase. Think about it for a moment. Mother Nature, the Creator designed us. Absorption ain't gonna wait to get out here to start. The drug is gonna be absorbed right from the beginning. So yeah, this is still the absorption phase. This is still the post-absorption or the elimination phase. Okay. So in the flip-flop model, okay, this curve still goes up because the absorption during the absorption phase, the absorption of the drug, the rate is faster than the elimination rate. So again, these are not elimination and absorption rates, these are the rate constants. Remember, the rate is always a rate constant times some amount. The rate, these are rate constants. So I'm not saying that the elimination rate is always greater than the absorption rate. I'm saying that the elimination rate constant is greater than the absorption rate constant. Did I answer your question? What time?
Yes.
Linda. All right. So qualitatively speaking, the flip-flop model absorption, flip-flop absorption model looks just like the regular situation where Ka is greater than Kel. So how do you tell the difference? Okay. So there are a couple of things to consider. Now, unless I tell you differently, I'll give you enough information for you to discern a difference. This is what we're going to normally assume, the case where Ka is greater than Kel. Okay. Because if you're just looking at the curve, you can't tell the difference between the two. Both of them are going to have an absorption phase and a post-absorption phase, just like I just said to Linda and the rest of the class. So how can you tell the difference if we had to determine whether or not it was a flip-flop absorption model or the regular situation? Oh, and let me just say too, in relationship to Linda's question, is that in the flip-flop model, this is still Ka right here. Okay, this is still Kel. So it ain't like this is all of a sudden Kel and this is Ka. No. We're just saying that the rate constants, change in their respective values, but not the actual rate. So this still represents absorption of the drug. Okay, I gave you the rate equation the other day. Those rate equations still are the same, okay, as before. It's just the rate constants have an inverted value. Not the rates, but the rate constants. Okay, and I, throughout the semester, tried to discern between rate and rate constant. The rate is the rate constant times some amount of drug. Okay. So how can we tell? Well, one way we can get a good idea is that, remember when we were talking about GI physiology, and I don't think I told you this. I did tell you that the mean GI motility time was somewhere 3 to 4 hours. I mean, to pass through the small intestine. And I also told you that the stomach had a mean emptying time of, I think I said 0.5 to 2 hours or 0.5 to 3 hours. The bottom line is this.
4 hours.
Huh?
Said 30 minutes to 4 hours.
Thank you so much. Okay. So the bottom line, 30 minutes to 4 hours, John just reminded me. So if you look at the time that it takes for, the average time that it takes for the drug to leave the stomach, 30 minutes to 4 hours, like John just reminded me. Then it's in the small intestine for 3 or 4 hours on average. That's, anywhere, up to 8 hours, and some people it's even longer than that. So, just as a ballpark figure, if the half-life I'm gonna make use of the same graph, okay? So we don't know if it's the flip-flop model or the regular situation. So to try to highlight that question, I'm gonna say, is this line associated with KEL or KA? This line right now. I'm gonna say the same thing about the hour residual line. We get the residual line the same way we learned in lab yesterday, and we're gonna learn today in laboratory. So I'm gonna ask the same question. Is this line here associated with KEL or KA? It's got to be one or the other, right? Okay, so we don't know. So if we want to find out, first of all, because of GI transit time is normally somewhere between 6 hours when you add together the GI emptying time and then the transit through the small intestine. So in my notes, okay, you might see something different in your book or in the literature, but for us, we're gonna say, for the drug to go from the stomach, we're gonna allow that 4 hours or so, and for it to go through the small intestine, we're gonna allow an additional 4 hours or so on average. So we're gonna cheat and say, if this half-life out here, associated with this terminal phase, this post-absorption phase, if it's more than 6 to 8 hours, I'm just putting that right, 6 to 8 hours, because we know how to calculate the half-life associated with that post-absorption phase. If that half-life is more than 6 to 8 hours, then this post-absorption phase is probably the elimination phase. Why? Because most drugs are not going to have any significant absorption beyond 6 and 8 hours because of GI motility. It's going to end up in the colon, the large intestine and stuff where you usually don't have a whole lot of absorption. Does that make sense what I'm saying? So if this half-life associated with this terminal phase, this post-absorption phase, is greater than 6 to 8 hours, then usually that's not going to be related to absorption because absorption has a limited amount of time in which it can occur because of GI motility. You ain't going to have no drugs being absorbed 15 hours after I'm talking about the normal individual. That drug is 15 hours after the dose, the drug is at a place in the GI tract where it's not going to be absorbed any longer. Does that make sense what I'm saying? So what I'm saying to you, if the half-life associated with that post-absorption phase is greater than 6 to 8 hours, it can generally be assumed that that post-absorption phase is related to the KEL value and not Ka. Can we farm with that? I did say farm. That's what it means. Is that okay? TSU finds. Okay. So if this is KEL, the slope of this line is equal to negative KEL, then the residual line has to be Ka. Ain't no other choice. Okay. We okay? But now you might ask the question, well, Dr. Felder, what if the half-life associated with that post-absorption phase line is less than 6 to 8 hours? What if it's only 3 hours? That can happen. What if the half-life associated with that line is 3 hours or 4 hours? Now what? Now what? Okay. Well, there's another method, and students struggle with this, and I don't know why, but this what I'm going to call a gold standard method makes use of what you've learned about the IV bolus dose, the one compartment model with an IV bolus dose. We can compare this curve with an IV dose. So this is the second method. This is the gold standard. Okay. If we have an IV formulation, now if we don't have an IV formulation of the drug, we can't do the second method. We're just gonna have to, be stuck with what we have. But if there's an IV formulation and we wanted to determine definitively whether this phase out here was related to the KEL value or the Ka value, we could give an IV bolus dose of that drug. If I give an IV bolus dose of the drug, how many phases am I going to have? If it's a one compartment model IV bolus, how many phases am I going to have? No. If it's a come on sports fans, don't break my heart. If it's a one compartment model IV bolus dose, how many phases will I have? One. It's only one. You're only going to have one mono exponential line. I said if it's a one compartment model, I don't want to fool out two compartment model if I'm comparing it, because this is a one compartment model. There is such a thing called an absorption, a two compartment model with absorption, but we're not going to cover that. The math gets too complicated and I'll embarrass it. Okay. So most drugs can be covered by one compartment model. There are some drugs that we need two compartment model. Okay. So if I give the IV bolus dose of the same drug in an IV formulation, I'm going to have one single line, right? I'm going to draw it on the board, but I want you to think about it before I draw it. That one single line, if I look at concentration versus time for that IV bolus dose, here I got two lines, right? I got a residual line and I got a post-absorption phase line, right? In the absorption mode. If I give an IV bolus dose of that same drug, and you just told me we're going to just give one line, that one line is going to be parallel to which one of these lines? The post-absorption phase line or the residual line? Exactly right. Exactly right. If I give the drug IV bolus dose, it's a one compartment model. It ain't got no, we know we're gonna have a single mono exponential line, okay? And that line for the one compartment model, nobody doubt it, it's got to be associated with elimination. In the one compartment model, we don't have absorption after the IV bolus dose. We don't have this to deal with. So that line that we look at after an IV bolus dose when we look at concentration versus time is associated with elimination. Amen? Now, if you got that, if you're not just sitting here, you're here physically and mentally and spiritually, or whatever the case may be, then when I show you my little depiction of it, it's going to make perfectly good sense because I just walked you through what's going on. So, if I give an IV bolus dose, let's just say the IV bolus dose looks like this. If it's a high dose, if it's a lower dose, the excess would be down here, but they would still be, parallel to one of these lines. So I gave the IV bolus dose. Let me just say IV bolus. IV bolus dose. I gave that IV bolus dose. And that's what I got. When I look at the absorption data, the conclusion I will come to is that the slope of this post-absorption phase line is equal to the slope of that post-absorption phase line, the slope. I'm trying to get you to be more technical. Come on, not KEL. The slope is equal to negative KEL. I'm just trying to get you to say it right, okay? But that line is associated with KEL, but the slope is equal to negative KEL, so we can get KEL from that post-absorption phase line. I just wanted you to say it right. The slope is actually equal to negative KEL. On the other hand, are we all together? If we gave the IV bolus dose. But what if I gave the IV bolus dose? This is the other possibility. I gave the IV bolus dose and I saw this right here. Everybody see what's going on? IV bolus dose. And I saw that. Now remember, you just told me the IV bolus dose only got one possibility. That from the IV bolus dose, that data has to be associated with KEL. So now, what would I say about the slope of this line versus the slope of my residual line from the oral dose? The residual line from the oral dose is associated with what? From the oral dose, that residual line is associated with Ka or Ke? Huh?
No.
Look at the IV bolus dose. We know that the IV bolus dose has to be KEL, associated with KEL. So if the IV bolus dose has the same slope as the residual line, then the residual line has to be associated with KEL. In this situation, if I gave the IV bolus dose and it was parallel to or has the same slope as the residual line, then that residual line would be associated with KEL. So therefore, this post-absorption phase line would be associated with Ka. It would be a flip-flop model. You can't funk with that, huh? All right. Okay. I walked you through it. I diagram. When you get an IV bolus dose, you got one line. The slope of that line has to be associated with KEL. So if you compare that with the two lines you got from the oral dose, you can determine which one of those two lines from the oral dose is KEL. The other one has to be Ka. Come on, sports fan.
But at what instance would it turn like that?
What you mean, what instance? Turn.
Because you had it like this, and you were like, okay, what turn?
I said if. You could give the IV bolus dose, this could happen, or it's only two things that can happen. Either this can happen, I'm going to draw circles this time, or this could happen from the IV bolus dose. Yeah. You get an IV bolus dose, ain't number one of those two possibilities going to occur. Ain't number one of those two possibilities from the IV bolus dose going to occur. Is it going to look like the circle line or the X line? And based on that occurrence, you, being TSU's finest, you make a decision now whether that terminal phase is associated with KEL or KA. If the IV bolus dose I gave it and it looked like the circular line, we know that that post-absorption phase is associated with KA. If I gave the IV bolus dose and it looked like the X's, I know that that residual line from the oral dose is KEL. So this line has to be KA. Come on, sports fan, we can handle that, right?
Right.
We can handle that, right?
You just gotta say it straight, you know, force of direction is KA and then residual line is KL.
Yeah. Just imagine some dollars, $100 bill on the line or something. It'll come to you. Yeah, just imagine money on the lines or whatever. But with the KEL, with the IV bolus dose, it's only one possibility. It's only one possibility. With the oral dose, it's two, but your question is, that's why I wrote KEL or KA. You get an IV dose, you get this kind of result from an IV bolus dose. That's telling me that that post-absorption phase line is associated with KEL. It's telling me that. But if I get an IV bolus dose and it looks like these X's right here, that's telling me that the residual line is associated with KEL. So then that means this line has to be KA, or associated with absorption. So if it looked like these X's here when I gave the IV dose, this would be a flip-flop model, wouldn't it? That would be the flip-flop model, right? If the residual line is associated with the KEL value, and that's going to be a greater value for KEL than KA, then if it would look like the X's, that would be indicative of a flip-flop model. Or are you looking at me like?
No, sir, I'm saying, sir, is this considered your gold standards?
Is it considered what?
Gold standards, good flop?
I'm sorry, I'm not hearing you.
The gold standard is talking about, is this the flip-flop gold standard?
The flip-flop is not the gold standard. The IV dose and making the decision based on an IV dose is definitive, which I said could be considered a gold standard. The flip-flop model is not gold standard. It's just a variation on this model right here. Questions? Oh, one more thing. And then I didn't write the equation for the flip-flop model. Check out for a moment, sports fan. That flip-flop model. Let me let you in on a secret that maybe some of you all don't realize. And it just occurred to me the other day, and I'm trying to avoid it. Let's say hypothetically that you had to, we're every 2 weeks, right? Let's say hypothetically, I'm going to be stupid now and say that you had to be tested every day. That there was going to be a test every day. Test a day, then when you come back tomorrow is a test. Hypothetically, as a student, what would that tell you or suggest to you about the nature of the upcoming exam? Not just in this class, I'm talking about in any class. Huh? That instructor is more than likely, and this is one of the problems they say we have in our public school systems, teaching the test. In other words, if I want to test you every day, and I'm limited in time, it's a real good chance that instructor going to be teaching the test, which is, to me, one of the disadvantages, just one of the disadvantages of testing every 2 weeks. Because as an instructor now, we have to project in advance in order to be fair to the students, okay? Then I got to make sure that what I have on the test, because the questions have already been submitted, not just by me, but by other instructors as well, have already been submitted. And I got to make sure I cover it. Okay, I'm going to let it go right there, okay? But I've told you all the first day of class, okay? And I've said repeatedly in laboratory, I'm a small person, but I talk real loudly. When you hear me, then that means you got to bring your conversation to a close, and I'm gonna ask that you do the same, not ask, but require that you do the same thing for your classmates when they're asking questions or whatever the case may be. So it ain't about just Dr. Felder. It's about so we can learn the material, okay? So, with that being said, the equation, something that I find kind of interesting. The equation for this flip-flop model, F times D times KA, divided by V times KEL minus KA in the denominator. Okay, remember, KEL is greater than KA, okay? And then that's all times e to the power negative KA times T minus e to the power negative KEL times T. So notice those two exponential terms have changed positions too. But guess what? This equation, okay, will give you the same, I'm gonna say compare to our regular equation, which says that C is equal to, in the normal case, C is equal to F times D times KA over, that's an A, V. If you can't see this in the back, I'm just writing the regular concentration time equation. KA minus KEL. And then that's all times e to the power negative KEL times T minus e to the power negative KA times T. So that's the normal equation. Now remember I told you that the shape qualitatively of these curves are the same? Okay. Even though in this flip-flop equation, I'm gonna say flip-flop equation, this is the normal situation, where Ka is greater than KEL, normal. Both of them give you the same answer for concentration. That's why these curves look alike. In other words, you could calculate the concentration. You could choose a time, and you might want to do this just to prove it to yourself. You can choose any time you want to, put it here and here, choose a value for Ka, okay, that is smaller than KEL, because that's the flip-flop situation. Ka is smaller than KEL. Okay. Choose a smaller value for Ka. You might let Ka be 0.3, and let KEL be 1.5, reciprocal hours. Choose a time. Just say put 1 hour in there, something like that. Choose an F value. Choose any F value you want to between 0 and 1. Okay. Choose a dose. We already have set a Ka. Choose a volume of distribution. Calculate the concentration. Just do it for one time. Then come here and flip-flop it in the normal case. So with your KEL value, you're going to put that, whereas here you had Ka is equal to 0.3. Here, let KEL equal 0.3. And here where you had KEL is equal to 1.5, down here let Ka equal 1.5 residual hours. So you're using the same value, you're just changing them around for Ka and KEL. And calculate the concentration at the same time that you used in this equation. You're going to get exactly the same concentration. You're going to get the same concentration. So that's why these curves look exactly alike. Does everybody understand what I just said? You can choose any values you want to. You can choose the value we used in laboratory yesterday, where we had KEL was what, 0.1, and Ka was 0.3 in the laboratory exercise. 0.1, 0.3. Then come down here and let, instead of KEL being 0.1, let KEL be equal 0.3 and let Ka be equal 0.1. Choose a time, calculate, see you're gonna get the same value with both equations. I'm saying that to say ain't nothing super fancy about this flip-flop equation, except that in the post-absorption phase, since KEL is bigger than Ka, and by the time we get to the post-absorption phase, this term has disappeared. So that's why when we take the logarithm of both sides of the equation, once this term is gone, then that terminal phase out there has a slope of equal to negative Ka. That's what I want you to see. Okay? So it's easier to see that with the equation in this form than it would in this form right here. That's all I have. Oh, I know, no, one more thing. To really fine tune you for next week, there's some other problems. What chapter is that? Chapter 8. Yeah, we spent all the time just on the first problem. So we covered most of everything I need for you to be able to do come Monday. But just to fine tune you, there are some other problems in chapter 8. So take a look at those as you prepare for your examination. So number 1, of course, will be our big problem. But number two is actually an extension of number 1, and we do some of number 2 in the laboratory. Okay. So number 1, number 2, you can skip 3 and 4. So 1, 2, 5, 7, and 8. 1, 2, 5, 7, and 8. 1, 2, 5, 7, and 8. That should be good. Any questions?
What chapter is that?
Chapter 8.
No, the number.
What number?
I mean the page number.
Oh, I don't know. Let me see if I can find it. 202? Okay. Thanks a lot. I appreciate that. Okay, that's all I have. I'll see you guys on Friday.
Is this, this is it?
This is it this time around. Yes.
Can we use Monday to study?
Can you use Mondays to study?
I mean, Friday to study?
No, I'm gonna see if on Friday I can start on something else so I can do an assignment for next week in the laboratory. Are you actually advocating not having class on Friday? Y'all ask for a lot.